Thank you for joining us. I'm here to talk about how we implemented a systems engineering handbook that we developed with a fellow systems engineering team to take the concept of 3 different experiments from a scientist and use the handbook to define what deliverables were necessary to perform the system design and integration for the design and integration and testing of a ThinSat payload to support 3 experiments, which were the evaluation of battery thermal shielding, the spectrum analysis for radio uplink and downlink communication, and comparison of 2 electrical power systems. Then, using these deliverables, we worked together with the design team for the implementation, and then afterwards we performed a verification validation of an integrated ThinSat, which was provided for launch. Overall, our team is including the systems engineers of myself, Matthew Herman, and Michael Jordan, where we worked as the consultants for the ISATS process. We provided these deliverables to the team Operation Asteria, which was our design team of computer, electrical, and mechanical engineers. This was all made possible by our project owner, Dr. Peter Packowitz. Again, to clarify the roles of each team, our systems engineering team worked on providing deliverables for the first half and second half of the systems engineering V. We provided deliverables from the input of the scientist all the way to defining requirements and informing the design for the design team. The design team performed the design and implementation from those deliverables, and then we moved into verification together and then validated the payload and provided that payload for launch. The integrating science experiments on the ThinSat process that was defined by our fellow systems engineering team defined processes, deliverables, and review points necessary over a 3-phase process to meet certain requirements for the ThinSat launch vehicle and NASA requirements. Also lists the different systems engineering tools needed, such as model-based systems engineering tool. We used Innoslate. Also a simulation tool for orbital profile, which was Systems Toolkit, and then some trade-off analysis and failure assessment. The ThinSat launch overview covers how Virginia Space provides its ThinSat bus and launch for $30,000. This is relatively cheap for getting a satellite into orbit, and this is because the ThinSat is integrated as a secondary payload on the Antares, where the primary payload is to deliver the Cygnus cargo vessel to the International Space Station. The ThinSat itself would be released in orbit, having a mission life of approximately 5 days. On the launch, it will experience sound pressure and vibration, and then in orbit it will experience thermal cycling from -30 to 60 degrees Celsius and vacuum at 10 and -8 torr. Again, this extreme low Earth orbit range is in an altitude of 100 to 300 kilometers. The overall of the ThinSat is it weighs about 280 grams, and it experiences about 90-minute orbits in extreme lower Earth orbit. The payload that is customizable by the team is limited to 55 grams, 100 milliamps of current, and a volume about half that of the ThinSat itself. The ThinSat will collect data and transmit over a third-party satellite relay link to an online user interface, Space Data Dashboard, which is provided by Virginia Space. Here you see the ThinSat payload that we designed overall with all teams, and shows each experiment and its space on the payload board. We had to provide handbook deliverables for the payload design for each experiment, ranging from the mission request form, problem and need statements, concept of operations, mission requirements, schedule, requirements definition, hazard analysis, fault tree analysis, failure mode and effect analysis, and our trade-off analysis. For experiment 1, here we show the concept of operations for the evaluation of battery thermal shielding. Our inputs were solar radiation, vacuum, thermal cycling, and earth radiation. From these inputs, the thermal shielding would affect the temperature inside the installation and outside the installation, and we would measure that difference and its performance throughout the orbit. And from that temperature, we would determine if the temperature inside the installation stayed within our ideal temperature range provided by the scientist based on all the inputs provided. One of the things we did to help inform the design for this experiment was designing a simulation based on a ThinSat model. We used Systems Toolkit, which provided an environmental profile for radiation, temperature, and orbital cycling after we defined the CAD model of the ThinSat grouped together with 3 ThinSats altogether for this simulation profile. The results from this simulation for experiment 1 showed the radiation penetration based on the thickness of the frame and the shielding, and this was able to inform our design and requirements. For experiment 2, here is our concept of operations for spectrum analysis for radio uplink and downlink communication. The idea of this experiment is that ThinSat will be orbiting an extreme low Earth orbit where the frequency and noise in that area is relatively uncharted. The ThinSat will be recording frequency and noise in the amateur radio band in order to provide a map of frequency and noise data over the Earth. This will allow future missions to determine potential frequencies for uplink and downlink communications directly with a ground station. Specifically, in this case, we're looking at uplink and downlink with the George Mason campus. Here, we use the simulation to compare a satellite relay link and the direct link, which would be at George Mason University. The main focus here is to look at the difference in the communication range, which would be greater for a relay link, and the signal quality. A better signal quality would be signified by a low bit error rate. The simulation output from this experiment showed that there was a higher bit error rate, therefore a lower signal quality with a relay SATCOM. Therefore, this helped validate our decision to provide a direct SATCOM link. For experiment 3, here is our concept of operations for comparison of 2 electrical power systems. Again, our inputs are solar radiation and thermal cycling in orbit. We have 2 different electrical power systems, MPPT, maximum power point tracking, and DET, direct energy transfer, which have their own solar cells as current generators for this experiment. We'll compare these 2 electrical power systems using current, voltage, and light sensors, and using this data we'll determine the voltage and current peaks, which will provide information necessary to determine maximum power point peaks for each electrical power system, and then we could determine efficiency of each power system. Then, following the implementation of this design, we will provide handbook deliverables necessary for system integration and testing. We will have to verify our mass, power, and size budget as provided earlier from deliverables, and as you see here, our mass was within our limits, our power was below expected, and the payload board fit perfectly in the ThinSat frame. You can see how we allocated space here. We developed a vibration testing profile based on NASA requirements. You see here our prototype profile and our minimum workmanship, which was our final flight model profile, which was provided as input to the vibration table. This was provided in MATLAB code, stepping up in frequency from 20 to 2000 Hertz. Following this test, we performed a visual inspection, verified no loss in mass, and performed operational testing following the vibration test to ensure the payload was still operational. For vacuum testing, we focused on the battery, which was our most vulnerable component for decompression. This test was based on NASA requirements, and we ensured that we tested the payload below 5 torr for at least 1 hour. Again, we ensured no change in mass, no change in depth, which ensured there is no deformation and no leakage of electrolyte. And finally, we performed ground testing with thermal cycling, which was performed under a heat lamp and ensured data was being sent from each experiment and was being collected properly on the space data dashboard. This was verified by having independent sensors next to the space data, next to the ThinSat itself, and then comparing the data from those sensors to the data collected on the space data dashboard. This was used to verify each experiment and validate the data being collected for the scientists. Here you see our overall ThinSat Payload program milestones. We have finished our PDR and CDR with Virginia Space, and we have delivered our engineering model for the balloon launch. Now we are awaiting results from that balloon launch in order to determine if any redesign is necessary before sending our payload for launch in April 2020. Thank you.